This is Mrs. O'Neill for AP Chemistry, Chapter 6, Section 4, the wave behavior of matter. Your objectives are going to recognize that matter also has wave-like properties and to determine simultaneously the exact position and motion of an electron, and that's that Heisenberg's uncertainty principle. So you should have watched that intro lesson on Dr. Quantum's double slit experiment. Here are my notes. When light passes through or reflects off a series of thinly spaced lines, it creates a rainbow effect because the waves interfere with each other. So this was all about interference. So a wave moves towards a slit, and what happens is it becomes a curve when it comes out the other side. How about with two holes? Well, there's going to be two curves. So now those curves, though, are going to start interfering with each other, and that's what this is called, where the crests kind of overlap with each other. That's where that interference comes from. So if you have several waves, you're going to have several curves and several interference things, and those are called interference patterns. And so if you go online to YouTube or anywhere else, you should be able to look up interference patterns, and you get all these cool patterns. So what will an electron do? So now remember, an electron has mass, so it also is matter. So a particle can only go through one hole, though, at a time. A wave goes through both holes at a time. So light shows us that we have this interference pattern. So this electron as a pattern, so we have here what we're going to call an electron gun. So we're going to shoot an electron or a particle through these slits. All right, goes right through. Goes right through. And it keeps going, right? That's where they're going. It goes right through. Okay. How about, keep going, building it up. But how about if it acts like a wave? Well, now look what's going on over here. Now it's coming up with an pattern or an interference pattern. So if our electron acts like a wave, this is what's going to end up happening. You're going to get this pattern like, oh, so it doesn't just hit the one spot over here and the one spot over here. It actually hits different spots at different times, and now you have this interference pattern. That's what's going on there. So that's how we can figure out or understand that these electrons not only act as a particle, but also act as a wave. So that's that interference pattern that this particle is going to form. So which did it do? Well, it made the pattern, so it acts like a wave, and that's how the Schrodinger's got his equation. So on to your packet notes. So this is Louis de Broglie, again, not the greatest with how to sound things out sometimes, but he was French. So if you know how to pronounce this in French, please come to class and say, hey, Mrs. O'Neill, this is how you say this guy's name. But I like to show you always pictures and when he was around and what he did. So pause the video, write in the words, and then play to hear mine. And of course, remember to read as you write. Don't just fill in the blanks. Make sure that you're reading everything. So of course, he called this matter waves. He said that wave characteristic of material particles also can act as waves. So give it some thought. Pause the video, read, see if you can come up with an answer. Did you come up with the word yes? And of course, all moving objects produce matter waves. And again, that baseball, even though it looks like it's going in a straight line because it's so fast, it really is moving in a wave. But they're so small, those waves, that we can't see them. So matter as a wave, again, we're going to use some velocity instead of frequency, and we're going to get this de Broglie's equation. This is not on your reference sheet, but now we can calculate that wavelength of an object if we really wanted to, like that baseball. So what will an electron do? Again, it goes through both. It makes that interference pattern that you just saw on that video. So it also behaves like a wave. It doesn't just behave as a particle. Now we can say it also behaves as a wave. So we want to remember, though, that some matter, those wavelengths are just a little too short to even notice, just like that baseball. However, this limits us, right, for what we know. So we don't know how the electron is moving or how it gets from one energy level to another, right? We know that the electron is a particle, we know that it moves, and we know that it's in a wave-like fashion. However, we really don't know how it does that. So we really don't know both the position and the momentum of an object. It's really difficult. We can figure out where the position is, we can figure out where the momentum is, or the velocity, right? But we don't know. It's really hard to get both at one time. So that's where Heisenberg comes in. Again, a little information on him. And of course, some of you might watched Breaking Bad. So of course, that's where Walter White got his Heisenberg nickname. So he came up with what's called the uncertainty principle. So again, for an electron, it's impossible to know both the momentum and the exact location of that electron and where it actually is located. And we also want to remember that all matter is constantly moving. So is that electron in an atom, right? So think about how tiny an atom is, think about how tiny an electron is, and so we can only just theorize. Again, we're still in the theory mode of where those electrons are when we did the electron configuration, right? Those are just a stepping stone, or let's say a theory, right? It's definitely a theory as to where those electrons are, but we're not 100% accurate yet. So here's the mathematics of it. Again, we don't need to really know this information, but I know some of you guys are really mathematical, or with your calculus, this might make sense to you. But we do not need to know it for your reference sheet. It's not on your reference sheet at all. So again, give it some thought, pause. Hopefully that makes sense. All right, we will see you in class.